Okay. Welcome. Sorry to be late. How's the homework going? Who's actually worked on it? Raise your hand. Everybody? Almost everybody? Okay, good. Don't leave till the last minute. It's not like 5 minutes worth of work, right? No. It's a lot of work. It's not like, there's a lot of work in it, I think. I don't want to pretend like there's not. It's pretty conceptually easy. I think you've been following the lectures and things like that, but implementing it can be tricky. Getting it right can be pretty tricky. Do you have any questions on it before we launch into the next lecture? Who's been going to the TA hour for help? Anybody? TAs, have they been coming? Some people?
Someone.
It's going to be like Friday, everybody's going to try to rush in.
If all of them come on Thursday, they will be class.
No, his class.
Yeah, exactly.
All right, cool. Let's see. All right, well, the homework is due on Friday by the end of the day, about 11:59 p.m., right? So get it turned in. There's a penalty for turning in late after that, so don't let it go further than that. So we spent the first part of the course just doing some basics and talking about some basics around neural networks. And today starts like sort of the next part of the course where we get to not so basic things. I mean, today will be the basics of convolutional networks, but we're going to start to move into things that are a little more complicated than just fully connected networks. And I'm excited. Hopefully you're excited. Yeah, I was excited. Thanks for the cheer. And yeah, should be good. So let's get started. Yes, convolutions. So I want to just start us with a little bit of history. This was put together nicely in some of the slides that I have been using, and it's kind of nice to see. So like, we haven't used the word perceptron, but another name for a fully connected network is a perceptron or a multi-layer perceptron. And the word the name perceptron goes way back to this guy Frank Rosenblatt back in the 50s. He actually implemented this like interesting, like definitely an old school machine that could produce a 400 pixel image. So like so all these early applications, image applications, were for reading text. It's like, could we teach something to read written text? So this is what this did. So it would like shine a camera. It would like, I don't know. I'm not really sure about the lights over there, but maybe like lights lit up when certain neurons were activated or something like that. But it's like basically the very first implementation of like this very simple network, this very simple linear network with a gradient update here, a gradient like that. And so yeah, so neural networks maybe go back to the 50s, probably before that in other form. I mean, they're just linear classifiers stacked together with some other reasons. But this is definitely well known. There's something way more complicated than this in the 80s. It's got a cool name, maybe even cooler than perceptron. Neocognitron. It's awesome, huh? I don't know what they were thinking, but yeah, neocognitron. So this is thought of as like the first convolutional network. It's not exactly convolutional, but there are definitely ideas in here that we'll be talking about today about what makes a convolutional network. And I don't know much more about it other than this was again used to learn to read written digits. So that hasn't changed much. We get backpropagation, at least becomes popular in the 80s as well. So in this paper, 1986, is I guess will attribute the popularity or the rise of the use of backpropagation over like some of the other methods that existed at the time and still exist today, but for training these things. So you get that around this time. This is called LayNet. So so I think I mentioned some of these names before, but there's like 3 big names like in early neural network research. Jeff Hinton, who wasn't on this paper, but then 2 other ones, Yashua Bengio and Jan LeCun. And they have this like really early convolutional network for doing document recognition. So again, it was like when you read text and read from the entire document. I don't know how successful it was, but it's definitely like one of the well-known this is thought of as like one of the first modern convolutional networks in terms of how its architecture was put together. These were hard to train. They were really hard to train for the reasons we talked about last time, or 2 times you know what about. We're talking about activations and saturating gradients, vanishing gradients, and things like that. But nevertheless, they got some results out of it. Probably could read some stuff. They could classify the documents or whatever. It was really hard to train these things. And then Jeff Hinton, this other name, the trio, he came up with this way of being able to initialize the weights in a deeper network. So a lot of these networks weren't super deep, but he came up with this way of this like unsupervised learning way using models called restricted Boltzmann machines. Anybody know what that is? Anybody like a physicist or did energy models and Boltzmann machines? No? Okay, well, it's all right. Restricted Boltzmann machines are pretty simple models. Anyways, you use these to greedily pre-train the weights from the inputs all the way through to the end. In this case, this is an autoencoder, so image in, you're trying to like basically recreate the image on the output, but compress it down to a much smaller representation than like the full image represents. And yeah, these kind of techniques sort of started working. It's interesting. I was doing my PhD this time. I remember like hearing about these things and thinking like, wow, that whole thing sounds crazy. Never mind about that. I'll just stick with my ODEs. They're really powerful. Yeah, here I am doing this. So it's a joke's on me, I guess. But yeah. So like when people wanted to do these, you have like just a couple of layers, and you do all this. It took forever to do all this pre-training. They still had like sigmoid type activations. Training was still really slow, but at least what this was doing was like putting the weights of your network someplace in parameter space where you could, like, it was a good starting point. You could go from there and find through gradient the second backpropagation algorithm, find a good solution or a good set of weights for doing this. And so, this isn't like an awesome recreation. You can see in this particular example, the decoder is pretty, blurry but it's doing a pretty decent job, and I thought it was as a success. And so a bunch of work continued to go into this, and then like in 2012, this is really when people went, oh my gosh, people are doing neural networks and they're doing real things. In fact, this particular architecture right here, there are a couple different papers that came out. You can see Jeff Hinton's on 2 of these ones being named here. One from 2010, but like this one in particular, ImageNet, there was a competition. I'm actually not sure if it's still going on. I think it's still going on. It's just sort of like not as interesting as it used to be. But at CVPR, one of these major computer vision conferences, they had this competition which had all kinds of vision tasks. And one of them in particular was like, classifying on a data set called ImageNet, classifying the objects within these images. And you probably know something about this. Pretty popular, pretty well known, and lots of techniques. But also in 2012, these guys show up with this convolutional architecture which is now called AlexNet. Alex is first author on here, and it won. It won by it won by a lot. Like in the sense of we have another history lesson like coming up, and we'll go through the numbers on this. But yeah, like it cut down like error from like I can't remember like 30% down to like just around 20% or like something like 15 to 20%. I can't remember exactly, but it was like huge. And everybody was like, oh my gosh, how did that happen? And what's funny is that the paper, when it was published, this is a picture of the architecture, but like it probably feels weird to you. I've seen it now a couple times in this class, but like the top part's chopped off, and it was actually published like this. Like there was a mistake made, and like when they published it, this part of the image was chopped off, and it's never been republished with the actual image. So like this image with the top chopped off is just a part of like neural network history, and now you're in on it. Now you're in on it. So yeah, AlexNet has the top chopped off of it. Yeah, and there's this interesting picture over here that we'll talk a little bit more about later. But basically, they were showing. This is a picture kind of showing what the different like layers in this convolutional network were learning, like what kinds of things it was learning to do with these color images. Okay, cool. So here it is again. Yeah, this is what I want to make the point about. Top chop. Yeah, AlexNet, top chop. Cool. Okay, nowadays you probably heard a lot about it anyways. And probably one of the reasons why you're here is just like the major success of convolutional networks. They do all kinds of stuff really, really, really well, like impressive things. And we kind of, at the beginning of the class we kind of talked about some of these things, but this ability to like segment it, to recognize objects in an image, but also to like segment the image to show where those objects are, label them appropriately, learn like really impressively accurate masks for these different kinds of things, like in that segmentation picture up there. Yeah, it's really amazing what these things can do. Yeah, you can drive cars with them apparently. You can do all kinds of cool stuff with them. So, for instance, you can do pose estimation. I think this is a really cool application. Like this thing has learned how to basically arrange these bars to tell you where the arms of this person are in this image and where they are relative to like the middle of the chest and the fingers. I mean, that's pretty cool. I mean, you see, like these are all really, really, really different images, right? They're very different from each other. I mean, it's the same guy, I guess. So I think it's not so different, but the poses, like different poses being made and different backgrounds and things like that. And yet, it still does a really amazing job of estimating where all that is. Convolutional networks come into play, and while playing video games, you might have heard something about reinforcement learning, how it's learned how to basically beat all the old Atari games, and of course, more important games like chess and Go without any problem. And one of the aspects of doing that is being able to like take the state of the game given by like the screen plus maybe a couple other numbers like the score and how many lives you have left, things like that. And being able to use the convolutional networks to say like, okay, like interpret for me what is going on in the screen at this time, and then help use that to make a decision about what to do next, how to move the joystick or which chess or Go piece to do. There's more like interesting or important things happening with convolutional networks, like being able to detect when a tumor is benign or malignant, being able to detect like certain like astronomical or cosmological properties of galaxies and things like that. And anytime you have a picture, you can basically like do something with it. In Recursion, we take pictures of cells and we use convolutional networks to identify diseases from the signature of the way these cells work, or the way they look, and then be able to use that information to say, like, when does a drug applied to the cells actually look like it's treating and rescuing the disease. Again, it's just, the reason we take pictures there is because we're counting on the power of convolutional networks to create representations of these images and be able to use those in such ways that we can answer really difficult questions. Yeah, lots of examples. We looked at this one early on too. This is cool. Being able to look at an image and have it write a caption for you. So lots of great stuff. You can even create art with it. All right. So let's get going here. So we've been looking at fully connected networks. So a layer in a fully connected network looks a little bit like this. You have some sort of input, and if this is straight from like an image, the image might not be in a vectorized form, but we vectorize it if we're looking at multiple layers within a fully connected network. The layers after the input are always vectorized just by the way the architecture works. But basically, you have some sort of vector input. You multiply that with some weights, and you apply a nonlinear activation to that. And we talked about sigmoid is bad, rate is good, and lots of other things. But that's basically what's happening in every single one of these fully connected layers. Is that you are producing for every row in the weight matrix for that layer, you're producing a number that represents something about that image, whatever the weights are trying to have learned to represent. In a convolutional layer, it's similar. I should say that, just point out again that the number that's showing up here in the output of this layer is I said it's the input multiplied with a row of the matrix, of the weight matrix. That's just a dot product. And with convolutional layers, it's similar. It's just that we have more than just a matrix or a row of matrix that we're doing dot products with. We have actually tensors of data. So tensors is just a fancy way of saying matrices. Like the idea of arrays of numbers with more than just two ways. I'm avoiding using the word dimensions since you can talk about the number of dimensions in each way in the matrix. But there's like basically two ways you can go in this array. And tensors just have 3 or more. So like an image is already like one of these nice tensors, right? It's a third order tensor, and like a matrix, it's got a width and a height, but it's also got some sort of depth. And then in the color image, RGB image, you have one slice here, one matrix slice here for each of the colors. And a convolutional layer, instead of like requiring you to like stretch that out into one long vector, what it does is it says, okay, I'm just gonna treat this like it is, and instead of learning weights that are like arranged in a matrix, each row representing some sort of thing that we've learned, we're now going to keep these things in tensor form. So the weights sort of come like this in these nice compact tensors that we call filters. One other aspect of the convolutional network is that these filters spatially are usually small. So this shows a 5 by 5 by 3. So this thing that we're going to like convolve or do dot product with our input is again not like stretched out, but it's kept in this compact tensor form, and it's small spatially. And the idea of these filters is that they are trying to learn like local properties, like spatially correlated local properties within the image. And what happens is this thing gets slid over, and I have some more slides on this, maybe I can point it out a little bit better. What happens is that you're taking this filter and you're doing a dot product. Hold on. Before I start saying that, let me just point out that these filters, when it comes to the depth parameter, the depth dimension, it's always the same as the image. When we do these, so spatially, so we think of like the first 2 dimensions as like the spatial dimensions, like width and height. But the depth is this like third thing that's kind of new for us. And our filters will always have as many dimensions, or what are called channels more commonly, as the input itself. And we're really, was there a question? Yeah.
So you would never look for features across channels? Or no, never mind. I guess you could still.
This is convolving always across all channels. And this is just like standard. I have never seen architecture that doesn't do this. And here's what happens, right? So like in the case where we had a fully connected layer, we have a matrix times the input. Here what happens is for any place we set this filter down within the image, we do this very large dot product. Basically, we lay this down so that the entries within this filter are directly over some portion of the entries within the input, and we just do an entry-wise multiplication of everything, just matching up where this thing is sitting down spatially, and then we add those all together. So like a dot product, it's like a bunch of entry-wise multiplications, and then you add everything up, and that's the result. That's the thing you get out going into the next layer when you do this multiplication. Yeah.
Is there a standard for choosing filter size, or?
There's not a standard. We'll talk a little bit more about shooting those kinds of choices a little bit later, but they're typically small. And the reason that they're small is that you typically learn a ton of filters. You learn not just one filter per layer, but you learn a ton of filters per layer. Each one trying to capture some sort of spatial correlation within your image, at whatever level of abstraction, whatever layer you're in. Often to that we might add a bias as well. So it might be some value B that we'll also learn, just like we've done in the other cases where you add some sort of consequences. So this looks very, very much like what we've been doing in fully connected networks. It's just that when we do these dot products, we just have tensors of things that we're multiplying together. So what happens is when we take this filter, this 5x5x3 filter, and we put it in all the different spaces that we can within this. In this case, it's 32x32x3 input. Each time we put it down, we get a new number, and that number sort of it's in a position. You can think of it if I put the filter down right here, then a number comes out, and that number sort of goes over here in this top corner, and I move if I move that filter over just one pixel to the right, then I get whatever number comes out is there, and as I move it around, I sort of fill up this other map, this output that we call, it goes by various names. It could be a filter map. Here, we're calling it activation map. Usually the word map is used here to indicate this output from a convolutional layer. But yeah, so what you're getting is when you do all these higher dimensional convolutions, these higher dimensional dot products, you get all these numbers out, and they get arrayed into a matrix. Again, because we have done it, the depth of the filter is the same as the depth of the input here, and so we only this kind of gets. If you think about it, this is getting compressed out. The depth is getting compressed down. There's 28 by 28 because if you slide this 5x5 over there, you'll see you get actually 28 outputs as you move that across. So you get this activation map. And it's also called activation map. It's also to invoke the fact that we've applied a nonlinearity to the linear output. Right? So we do the dot product, apply a nonlinearity, and get this activation map. And that's the output from this layer, and that becomes the input for the next layer. Now it's only producing a single filter, a single channel here, one activation map. But what I said before is that we're actually going to learn a ton of filters. So we actually might learn a second filter, and that gives us another activation map of the same size. We use the same size filter. We get another activation map of the same size. And so now this output is becoming a tensor. Everything's got the same height and depth, but we're now going to width and height, but we're going to keep adding depth. And we can just keep learning these. We can just basically choose however many filters we want to learn at this step and get that many activation maps out into one stacked up, what this has in quotes here is a new image. It looks kind of like the input here, because it's like in this order 3 tensor. But it's the output of convolving this input with, in this case, 6 different filter maps.
So when you're doing the
Filters. So.
when you're doing the dot product of the filter with the image, are you doing it across all the 3 channels?
Yes. Remember, the filter itself has the same depth as this does right here. So when you do that entry-wise multiplication, all the numbers within, across this depth, they all participate in that, and then you sum it all up.
So these are all different filters.
Yeah. So so the output here, each one of these matrix slices is from a different filter, is running a different filter across the entire image. Left to right. Good. Yeah.
And the different filters are like different activation functions?
No, you typically use the same activation function. Okay. It's just that, like the weights within that filter, you're learning they're different.
Oh, okay.
Yeah. So instead of learning how we learn this, we would learn this matrix in the fully connected case to take us from the dimension of the input to the dimension of the output. Here, you are learning like a whole bunch of those in one layer.
Okay.
And you could have done the same thing in the other one, but it doesn't really make sense because then you're going to have tensors there, and you wouldn't have a way to deal with tensors in the fully connected case. So, yeah. Yeah. Question. Another question. Yeah. So like this is like the basic thing that's happening in the convolutional layer. Is again. Learning a bunch of filters that then give us another tensor output, and we stack those things up. And yeah, so I mean, this is all about like architectural decisions of what your network looks like. But if we start with input like this, so 2 by 3 to 2 by 3, we apply convolution. That gives us so 6. We learned 6 filters, 5 by 5 or 3 filters on this. Then we get an output 28 by 6. We apply the ReLU. We apply some nonlinear activation to that. So ReLU is an example in this case. And then this is now our input to the next layer. So now we do a convolution. Our filter this time has to be, the spatial dimensions we have control over, but it has to be that the depth of these new filters is 6 because the activation maps here, we have 6 of them. And we just keep doing this. So like in this case, this has us learning 10 5 by 5 by 6 filters. So that gives us an output of 24 by 24 by 10. So what would the filters have to look like in the next layer? What would the depth have to be? 10. Yeah. It's always got the depth of these filters has always got to match the depth of the input.
So from this pattern, it seems like there's eventually a hard limit on number of convolutional layers you can actually have.
Given like an initial size of the image.
Yeah, exactly.
Yeah, so like this depends on the initial size of the image and then the spatial dimensions of the filter exactly. Like, at some point it's going to get down to like 1 by 1 if you keep following this. Or you could pick the dimensions wrong and like try to do a convolution with a filter larger than the actual size of the activation maps. That would be bad too.
So on a similar note, like how many convolutional layers do you tend to see, right? Like what's the ballpark range?
Well, we're gonna next week we're gonna go through kind of like the history of convolutional networks, and early stuff was maybe 10 layers. There are convolutional networks that have thousands of layers. No one really trains those much, but like it's very typical to train networks with 50 or 100 layers.
Okay.
Yeah, and the sizes of these filters matter in that case.
So why don't you just pad it so it's the same dimensions each time?
Yeah. So padding is something that we'll talk about. So if you want to make them the same dimension each time, then you do something called padding. We're going to talk about that like really soon. But it's typically the case that these activation maps, even with padding, you typically you make choices. You make choices that do make the activation maps spatially smaller. You're trying to concentrate information into smaller and smaller arrays of things. That is an interpretation of learning. It's like taking whatever information occurs here in this very large dimensional input and compress that down into something spatially and also maybe in terms of filtering size much smaller. But yeah, there's other techniques for doing that. They're called pooling and stride, and we're going to talk about those things today. Other questions? Yeah.
So, maybe I don't quite understand it, but what's to keep from each of these filters becoming the same, like, wearing the same lights, or
Oh yeah,
becoming the same?
Your question is something like, why? Like, how do you prevent it that this is like there's six filters here, but they could all be like the same filter, right? That's like,
Yeah.
So there's nothing like necessarily like built in to say like let's prevent that. But what happens when you train these things, you pick your loss function, like we're doing a classification problem, and when you train these things to do that classification problem, it tends to use all the filters to do different things because it's building up features for the final classification from all of these filters. And so you're right. There's like nothing like just like in the way that the problem gets set up that guarantees that. And sometimes, like if your model has too much capacity, it might be the case if like two filters are the same. But that rarely happens. It actually ends up using all the filters to do different things because you see if these filters are the same, it gets redundant information and it doesn't use that. It can't use both of those things as well as it can use if they provide different information. So just the fact that it's trying to like do an optimization problem, it's trying to like minimize the loss of something, that typically forces these filters to be different. And in all the examples we look at, they're very different. It's trying to learn features about this image that allows it to do whatever task it's trying to optimize for. It's optimizing for. So in the classification task, it's trying to figure out ways to aggregate or compress the information down in such a way that through various layers of abstraction, through various layers, to in the end just have a couple of features that you can easily classify.
Do you ever pick and choose which filters or do you solve or like, I don't want this filter, how do you use this filter, anything like that?
Do you, like once it's trained, do you choose which filters you want to use?
When you kind of first, let's say you pick one of the weakness that's meant for image classification or something. Probably you have this probably processing some signal. Can you just pick and choose and replace some filters?
Okay, so what you're saying is something like you might come to this problem knowing some good filters, and you want to use those and not have them be like trainable, so that the filters have changed in some way. Is that what you're saying? Yeah, definitely. So you can like what might be done in that case is you'd have a network that would learn a bunch of features, and before it gets to like in a classification problem, before it gets to the softmax layer to do its classification, you might concatenate with that whatever like manually extracted features you have come up with. So you have like learned features and these manually extracted features from whatever filters you like best. And then you put those two things together, and then you do your loss. And the reason why you put them together at the end is one, you want them all to contribute to classification, but you also you don't want like your learnable features to replicate the information that's in your other ones, in your extracted ones. And there's like lots of ways to do that. There's like there's better ways than just concatenating. There's like ways of bringing in context, stuff that you know about the images, into the architecture here itself. It's kind of like a little bit beyond where we're at right now. Especially here.
How would somebody go about deciding how many filters to use for a particular layer? Like, what implications does that parameter have?
You'll see as we go through the history of these things that there's not really like I'll tell you a rule, like double the number of filters, like every once in a while.
All right.
And then do that until you get like enough. There's no theory around these kinds of things. There's not. I mean, there's some basic understandings of things you should and should not do, but like optimal number of filters, there's not a way of doing that.
So, say you have like picture recursively, like how would you say these filters are pulling out that recursive line? Is it creating like maybe a linear combination of different people so that you can classify that person, or is each filter saying?
We're going to watch a video here in a second from a friend of mine, Jason Muzinski, that does a really good job of kind of like giving you some idea of what's going on here. But it's really hard to know what's happening. But what the video will definitely help to kind of make you think about the possibilities of things that could happen. But it's really hard to say like for any neuron, like at any layer, like what exactly is happening. It's just so like typically what happens in like the first layer is you learn edge detectors. Your filters learn to like detect edges of things. So you have like they're known as before filters, but basically it's like like in multiple colors you can detect this kind of an edge like at this angle or at this angle or like horizontal or vertical or like circular edges or whatever. I mean there's like lots of things like this across like a color spectrum, and they like if you have like a 32 by 32 is a little bit unrealistic for like images that we might think about, but like 5 by 5 filter, like a 3 by 3 filter on the image that's bigger, you're only going to capture like a small part of the image, right? So it's like learning to like in the first layer, it's like learning to like represent something like edges. And the next layer is learning to do something with those edges, like put them together in more complicated patterns. And then the next layer is learning to take those more complicated patterns, put those together in even more complicated patterns, and so forth. But it's really hard at any stage to say exactly what's happening. And there's no theory again to say like this is going to happen. But you can also be guaranteed that the first layer are these before edge detectors.
So if you're doing a problem that's like very similar to something that's done previously, could you like cut off the neural network like halfway through or early on and actually use some of the pre-trained pieces?
This happens all the time. Like none of it has to be similar. So like it's very typical to take like the winner of one of these ImageNet competitions. Mm-hmm. Take like the weights, like the architecture and the weights get published. Most of the deep learning frameworks then they have like what's called a model zoo, where you can go in and you can get that model, its architecture plus its weights. And then what you typically do is not just like cut it off and like halfway through, like you basically go all the way to the end of it. And then we'll talk about this in a second, but there's usually like a fully connected layer or two to go from like the convolutional stages to like the prediction stage, like in a classification, to go to the softmax layer. Mm-hmm. And you typically just learn those, like everything about the network's frozen. Like all the weights are frozen from input up to like the end of the convolutions, and then you learn the weights of those fully connected layers to do your particular problem. And it works extremely well. This is a technique called transfer learning. And yeah, it's like probably the most common thing to do, especially if you don't have like a GPU cluster to go retrain these like monster networks. Great question. Any other questions? Okay. Oh, yeah. So this is kind of what I was talking about. So this is a particular kind of architecture called BGG, and convolutional architecture. And these are the filters learned in the first convolutional layer, and there's 64 here, and they're quite small. But what you can see is you you can see like these, this is what it's talking about, these like edge detector things. So look at any one of these things, you see like horizontal, vertical, or like 45-degree angle patterns. And it's not perfect, but you see this a lot. You see this across like different colors and color gradients. These are used to, again, like pick out, it's like learning to detect edges within your image, because like if this thing is learning to classify images, like it wants to classify that as a dog, like the first thing you might think about doing, like just manually doing this, is to try to like outline the dog, right? And then like focus on the dog. And that's something like what's happening when you learn these kinds of these edges. But it can do far more than like outline. It can do all kinds of things with edges as you think about building them up. Now, 3 layers into it, so this is one, so like the 3rd layer into it, you now have built up out of this and then another layer in between. You have these far more complicated filters that look kind of like there's some edge stuff going on, but it's like a lot more complicated, and you can notice like how the colors are, very distributed throughout these things. So, yeah, I don't know how to interpret this. I see kind of like a football right here, but that's not what it is. Yeah, like it's really hard to interpret what these things are, and especially as you go now a couple layers down and look at the filters coming out of this layer. But yeah, like this is what's happening. It's taking very simple feature detectors, in this case edge detectors, and building those up into like much more complicated features detectors. And this, just to make a quick point, and actually but this is very similar to how we think like the human visual system works itself. As we go from like retinal cells through some of the early relay stations within the brain into visual regions like primary visual cortex, V1 and V2 and so forth. Actually, it appears to be arranged hierarchically. That there's networked to take the light impression on your eyes, and transfer that to various layers of neurons that are all connected locally to each other in the same way that these convolutional networks are, to then produce like detectors of things like edges. This is like very well known in neuroscience that we have cells, we have neurons in our brain that respond to like early on in the visual system to things like edges or like light edges or sources of light, and all the way up to some. This is I think still kind of like a hypothesized thing, although it's been shown that we have things like grandmother cells, which means there's like a neuron in your brain that activates when you see your grandma in the visual parts of your cortex of your brain. So like, it's not super well characterized, but like some studies have been able to kind of show that consistently there are neurons that fire when you look at images of like people you know or like famous people or something like that. And it could be that neuron somehow is like your grandma neuron or your Donald Trump neuron or your whatever neuron like that. It seems kind of strange. Like there's some problem with that idea, but it's definitely been observed. These things are called convolutions because they're a bit like, if you've ever done like signal processing, there's actually like an operation between 2 spatial time series called a convolutional operation. It's basically like taking one function and sort of like running it over the other function and computing the integral of the product of those things. So not like an important thing to have to memorize here, but this is where the word convolutional comes from. Yeah, we put these all together into a few layers, and voila, you can predict things like that's a card. We talked about convolutional layers, we've talked about activations. There's a couple other layers that we're going to talk about still, like these pooling layers, different types of pooling layers that are used to, again, aggregate information within these activation maps. But this is basically what we're doing. Oh, and that I should just point out at every stage here, you're getting like a more and more abstract representation of the original image. Until eventually you go from some like convolutional or spatial activation map to a fully connected layer where then you attach your loss function like softmax to do your problem. Okay, so this is the video I produced. I think this is a great video. So it's only like 4 minutes long. And I think I don't know about how the volume is going to work here. For some reason I can't turn this. The new MacBook Pro are so lame. Like the touch bar is so useless. And this is going to be loud as possible. I hope that we can hear this. I will probably stop it along the way. Jason Gozinski is a friend. He's an advisor to Recursion, and a couple of years ago he put together this interesting package for visualizing what's going on in your convolutional neural networks. And he put this video together. That's really great.
Recent advances in neural networks have enabled computers to better see and understand the world. They can recognize school buses and zebras, and can tell the difference between Maltese terriers and Yorkshire terriers. We now know what it takes to train these neural networks well, but we don't know so much about how they're actually computing their final answers. We developed this interactive deep visualization toolbox to shine light into these black boxes, showing what happens inside of neural nets.
So you get what's happening here? So there's a particular architecture happening here. This is very similar to what the picture we saw with the car on one side and the prediction on the other side. But we have like our filters at every representation of our filters at every layer as we go along here. So convolutional networks, pooling layers, activations, and column pooling activations, and so forth. There's some fully characterized. But the point is that he has up here highlighted conv1. So these are all the filters associated with the first convolutional layer in this network. So this is where input goes directly into this layer.
Top left corner, we show the input to the network, which can be a still image or video from a webcam. These black squares in the middle show the activations on a single layer of the network. In this case, the popular deep neural network called AlexNet from Eaton Cafe. By interacting with the network, we can see what some of the neurons are doing. For example, on this first layer, the unit in the center responds strongly to light to dark edges. Its neighbor, one neuron over, responds to edges in the opposite direction, dark to light.
See that? Interesting.
Using optimization, we can synthetically produce images that light up each neuron on this layer to see what each neuron is looking for. We can scroll through every layer in the network to see what it does, including convolution, pooling, and normalization layers. We can switch back and forth between showing the actual activations and showing images synthesized to produce high activation. At the time of using the fifth convolutional layer, the features being computed represent abstract concepts. For example, this neuron seems to respond to faces. We can further investigate this neuron by showing a few different types of information. First, we can artificially create optimized images using new regularization techniques that are described in our paper. These synthetic images show that this neuron fires in response to a face and shoulders. We can also plot the images from the training set that activate this neuron the most, as well as pixels from those images most responsible for the high activations, computed via the deconvolution technique. This feature responds to multiple faces in different locations. And by looking at the decon, we can see that it would respond more strongly if we had even darker eyes and rosier lips. We can also confirm that it cares about the head and shoulders, but ignores the arms and torso.
So pretty cool, huh? So like this is 5 layers in, and they've found a neuron that they can like have. They have a filter, an activation map they can like provide some understanding about, which is really cool. And I don't know if you kind of capture what's going on here, but this is basically showing that like it's saying which direction should this image go to make this map fire even more. And it's like he just said, like if they had bluer eyes or rosier lips, this would actually cause it to fire even more. So it gives you some like understanding, at least of this neuron, this activation map, what's going on. Okay.
We can even see that it fires to some extent for cat faces.
Once a rosier
Using
cat.
backprop or decon, we can see that this unit depends most strongly on a couple units in the previous layer CON4, and on about a dozen or so in CON3.
So it's showing
Now let's look at another neuron.
linears, like which neurons are
So what's
causing
this
this.
unit doing? From the top 9 images, we might conclude that it fires for different types of clothing. But examining the synthetic images shows that it may be detecting not clothing per se, but wrinkles.
So the synthetic images are these ones over here, and they look a lot like the filters we were looking at before. So this is like a way of saying what are the images that cause this to fire the most. And we typically think of this as like the interpretation of what's happening here. And so he was saying like these are the images. These are like 9 images where this map is most active, and it's all clothing. But when you look at the synthetic images that make this most active, you can see there's like texture, right? There's like this light, dark, there's like this sort of halo rainbow thing, and then within that, light, dark. So he's saying like, maybe the interpretation here is like, we're looking for texture within the image, possibly on clothing.
In the live plot, we can see that it's activated by my shirt, and smoothing out half of my shirt causes that half of the activations to decrease. Finally, here's another interesting note. This one has learned to look for printed text in a variety of sizes, colors, and fonts. This is pretty cool, because we never asked the network to look for wrinkles or text or faces. The only labels we provided were at the very last layer, so the only reason the network learned features like text and faces in the middle was to support final decisions at that last layer. For example, the text detector may provide good evidence that a rectangle is in fact a book seen on edge, and detecting many books next to each other might be a good way of detecting a bookcase, which was one of the categories we trained the net to recognize. In this video, we've shown some of the features of the DeepViz toolbox, and a few of the things we've learned by using it. You can download the toolbox at this URL and explore for yourself.
Okay. So cool, huh? So Jason's all about like trying to figure out, kind of provide interpretations of what's going on in these networks, and build a lot of cool tools. And usually at conferences, host or has organized like workshops around these kinds of ideas. So yeah, very cool. Questions about that? Questions about what you saw? Does that help to kind of think about what's going on in a network like this? I mean, you need some experience actually putting these things together, training and looking at them. But like, hopefully this gives you some idea of what's happening. Like, there's just this buildup from very simple types of filters to more and more complicated ones that do. We're not completely sure what, but that do interesting, very interesting things. Things that would be very, very difficult to like program like manually to do. This is one of the main things I hope you get out of like taking this class and working on home assignments and working on your project. There was a time when people tried really hard to like create manual features, to manually create features that they would hope would be good input to like some other kind of machine learning algorithm. And you know, it didn't do like it did do some learning, but not nearly as much or as impressive as like what's happening here. And the point is that we're creating these features like end to end. We go from input all the way through to our loss function, which gives us our optimization cost function, and just because of that, just because we do this from end to end, we get these really interesting things along the way. Like you pointed out, no one told this network that it should do this, and yet it did it. Because somehow it was advantageous for the final optimization problem to do that. And that's kind of getting like a little bit coming back to your question about like what filters, like what prevents these filters from being the same. It tries to use everything it can in the network to minimize that loss function. and it always does. Backpropagation allows it to happen. Okay, so coming back to these boring slides. After that video, these feel really boring, right? So, yeah. So let's think a little more deeply about what's going on in these convolutions. So, let's just take a simple example here, where we have 7 by 7 input, and we have a 3 by 3 filter. Now, there could be channels here. There could be a depth dimension here, but we're not showing. We're just assuming it's there, and this filter is actually of the same depth. Okay, so what we're doing when we do convolutions is we have this one filter, and we just sort of run it along in every direction, everywhere we can basically center this thing. We set it down. We can compute one number from that. And if you look at this, we can go 5 across. 1, 2, 3, 4, 5. We can go 5 down. 1, 2, 3, 4, 5. So the output from just doing what we did right here should be a 5 by 1 output. And then for every filter that we learn, we're going to add more depth to that 5 by 5 output. We might, for certain reasons, like reducing the size of this, and without the pooling, or without the padding, this kind of seems strange, but you're not required to just like move one pixel to the right or to the left or up or down. You can move as many as you want. And this value is called the stride. And so we can start with the same input size and the same filter size, and instead of moving 1 pixel to the right, we can move 2 pixels to the right. And we do that again. And we can also do that in the vertical direction. Then we would get a 3 by 3 output. So just by making a choice about the stride, we can actually change the output size of the activation times. What happens if we try to do this with, in this case, a 7 by 7 with a 3 by 3? What happens if we try to do this with a stride 3? Well, the first one fits. Then we move 3. Oh, I don't have it. We move 3. Then we move 3, and that would fit. So it would go right here. 1, 2, 3 would be there. But then I couldn't move 3 again. It would be like off the image, off the input image. This seems like a problem. But it's really not. Here's just some of the math that you might want to get comfortable with as you start thinking about the next homework after this one, which I hope will come out by the end of this week. But if you think about, this isn't always the case. It isn't always the case that we have square images. And it doesn't have to be the case that the filters are square, but the filters are almost always square. The images often are not square, but it's often typical to like resize the images, make them square, or to crop out a square portion of the image. But it's not totally necessary. But the point is that it's not too hard to think about what the output size will be if you have a square input of dimension of side length n and a square filter of side length f. Then basically your output size, the side length is going to be that formula, n minus f, that quantity divided by the stride, and do this plus 1 for the initial. So we can see, like in this way that we're doing it, we start with stride 1, we get 5 by 5, which we already saw. We start with stride 2, we get 3 by 3. If we do this stride 3, we get this like non-integer number, which is bad. But it's really easy to deal with. This was already mentioned earlier by someone talking about padding. What we typically do is we just pad the image around the outside of it with zeros. There's actually different ways you can do padding, but like zero padding is basically the most common, by far, way of doing this. But you just take your image, and however many zeros you might need to be able to fill up your image with filters kind of going across evenly, You just do that. So for both the filter size and the stride. And the reason for zeros is we're doing these like high-dimensional dot products, right? So when we do a dot product with a zero, that doesn't contribute anything, right? So when we do this dot product with these zeros, basically all that's left over, the only thing that contributes to the dot product is just what's within the image itself. Everything, the zero pattern, they don't contribute anything to the dot product because it's a zero. So that's what's typically done. So there's a pre-processing step usually when training these networks that will add zeros to your image, however many you might need. So how many might you need? Well, like I mentioned here before, when you do, so with stride 1, if you do this pattern, you can basically center your, like in this case it's 3x3 filter, center it at the upper leftmost corner, and just move by stride 1 by 1 pixel at a time. You can just keep moving along, right to left, up and down, and you get exactly the same size output as a result. So start at 7x7, because you do this padding, it allows you to put filters at the extremities here, at the corners, and that allows you to get an output of exactly the same size. This maybe sounds kind of funny, but it's not uncommon. And yeah, you do, depending on the filter size, you might need to pad with a different number of zeros. There's a formula for computing it. It's really pretty intuitive. Let's see. Yeah, so this same question was asked earlier about like this thing of shrinking. You don't have to shrink via the convolution if you do the zero pattern, which is great. So here's an example. Oops, too fast. Here's an example just to kind of think about this. So we have a 32 by 32 by 3 image input. We want to compute 5. We want to convolve on this 10 filters that are 5 by 5 by 3 with stride 1, and we're going to use padding of size 2 just because we've got a 5 by 5 filter. So that when we get to the corners, we need 2 zeros in a vertical direction, 2 zeros in a horizontal direction to allow us to do an appropriate convolution. So the question here is, what will the output size be in this case? Stride 1, which means that we're going to move by 1 pixel, either to the right, to the left, or up or down. We're padding it with enough zeros where we can put a 5 by 5 filter in any of the corners. So what is the output size going to be of just one activation path? Same, 32 by 32, right? What will the depth be of the final output?
10.
10, because we're learning 10 filters. Good. Great. How many parameters are we actually learning in this layer? So that's a different question from like the output, right? The parameters are the filters themselves. So how many parameters are we actually learning? You're saying what? Okay. Okay, 250 came from where?
5.
Yes, each filter is a 5 by 5, so there's 25 parameters within that filter. There's actually, we're not really pointing it out, I should say 5 by 5 by 3. There's actually a depth 3, so 25 times 3 is 75. So each filter is 25 by 5 by 3, has 75 parameters in it. There are 10 of them, so that's where you got to 250, or in this case, when you have a depth 750. And there's also a bias parameter for each of the filters that you're going to learn. So it gives you another 10 for each filter. So there you go. 750 plus 10 is 760. So if you think about that, that's actually pretty amazing. So like 10 filters 10555 filters only require 760 parameters. And there's like a lot that can be expressed in this thing. We usually use more filters than 10 when we're doing real convolutional networks. But you know, this is one of the powers of the convolutional network is if we were to do fully connected here, like 32 by 32 by 3, fully connected to like 32 by 10, we would have, you know, 32 by 32 by 3 times 32 by 32 by 10 parameters. Fully connected. That's a massive amount of parameters. Instead, what we're doing is we're saying we're not going to try to learn all of that. We're going to learn locally. We're going to learn local spatial correlations and apply that all over, like that same correlation. Apply that all over the image. And that way we drastically reduce the number of parameters, but we really we preserve a lot of the expressivity of the network. Yeah, I'll post this. Here's all the math if you want to like compute all the for rectangular tensors, the number of filters, and the filter size and stride and all that kind of stuff. It's not too difficult to calculate these things, but not worth going through right now since we only got 10 minutes. But I'll put these slides up and you can go through these. Yeah, people were asking earlier about like how do you choose these values for like the number of filters, the size of the filter, the stride, the amount of zero padding. Zero padding, that's just like you always just pick the value like what fits. So basically, when you use a deep learning framework like TensorFlow or Python or something like that, basically when you put the layers together, these kinds of things are usually just figured out for you. It's like automatic. What you like? There's a default value which is like preserve the dimension, the spatial dimensions, and you use things like strides, what we're going to learn about next, pooling, to reduce the spatial dimension. You don't use the convolution to reduce the spatial dimension. You use other operations to reduce the spatial dimensions. But yeah, like what are common choices here? Well, number of filters, yeah, powers of 2. Like it better be a power of 2 or else you'll look dumb. I don't know. It's just the way it is. Part of powers of 2, by the way, is like when you go to things like distributed training, when you're actually training on like clusters of servers, you typically will have powers of 2 number of servers in your cluster, and it just makes the math so much easier just to be able to always divide by 2 to like distribute things evenly. I don't know if I ever get to that in this course, talking about those kind of issues, but yeah, keep things powers of 2. It makes things super nice to be able to like go up in size and go down in size. And then for filter sizes, you rarely see things bigger than 3 by 3. If it's anything bigger than 3 by 3, it's usually like only at a very early convolution layer. So like ResNets, residual networks, is a very popular, very powerful convolutional network. Its very first convolutional layer has a 7 by 7 filter in the standard formulation of the model. But as you move down in layers, the convolution is either 1 by 1 or 3 by 3. Now, common choices of the filter size 1 by 1. That seems weird, huh? What is a 1 by 1 convolution doing? You can think of it as fully connected, but it's fully connected only like in the depth layer. So 1 by 1 convolution isn't doing any spatial convolution at all. It's only doing convolution like in the depth, like across the channels, and so it's like just think of it like you're learning like a linear, like a vector for each one of the pixels within your tensor here. So it seems weird, but it's done a lot. And the reason you do it is to go from one depth to another. It's a very simple, principled way to do this kind of transformation. Go like in this case, the way this was done, to go from 64 channels to 32 channels, preserving the spatial structure. So like not in a convolution. it's a convolution in depth, but like it's not a spatial convolution. So yeah, these exist. They're useful. They're in most modern architectures. Yeah, given the time, I'm just going to skip over how this is kind of like. Okay. Yeah, and there are fully connected layers, usually at the ends of these things to be able to learn, like, to have some place to attach your loss function. So there's one layer left that we haven't, type of layer left that we haven't talked about, this pooling layer. So there's this idea of pooling, and it's typically used like when you do a stride, I guess I just spent a ton of time talking about this, like when you do a stride 2, you are reducing the spatial dimension of your activation nodes. They're going down by like a factor of 2, because it's usually odd, so it's not exactly the factor of 2, but it's like, you know, divide by 2 and take the sigma. But so strides, taking a stride greater than 1 is a way of basically reducing the spatial dimensions of your layers, of your activation maps. So another way to do this that is very common, and it's common because 1, it's effective empirically, and 2, it's like very simple to compute. Convolutions involve all these multiplications and all these additions. You have this idea of pooling layers. The pooling layers do like what it sounds like. You're chopping up your image into little rectangular pools, and you're aggregating the pixel information within those pools. So in this case, there's some sort of, the pool is effectively doing some sort of downsampling in 2x2 pools. And so here's like a really simple way to think about this. So let's take one of the slices out of our input, 4x4. If we're going to do pooling layers also have the idea of like a filter size, and a stride. And in this case, we have this 4x4, we have a 2x2 filter, and we have a stride 2. So basically, we have these 4 pools that are colored differently. And a very common operation to do in these pools is just to take the max activation from within that pool, and that becomes the output in this activation map of lower spatial dimensions. Other common ones to do are like averaging. You can average the values within there. Max is used because max is really inexpensive to compute, and it's really effective. Like basically, if you think about this as downsampling, it's just saying like we're taking this 2x2, like in these 4 pixels, this 2x2 region in the image, and we're just replacing it with this maximum activation. So because it's such a small spatial space anyways within the image, like we would expect there to be high correlation amongst these activations. And we have a desire to reduce the spatial dimensions, mainly because it's costly to have high spatial dimensions in these convolutional layers. And yeah, we just replace it with the max, and this works great. And there's like basically all the possible ways you can think of aggregating these pools of numbers. You could use one of those things, but like regularly, max is just like the thing that's used. Except in the residual networks, they have a final pooling layer at the very end. It's this global pooling, and it's actually an average. But it's an average for a good reason that we will probably talk about next week. Yeah, so that's the idea of pooling. Pooling is like this very inexpensive way of reducing the spatial dimensions of the application. And here's some more math around that. So, so we're out of time. These are convolution networks. These are like the basics of convolution networks. And from here on out through like the next, I think it's 5 or 6 weeks, we're basically going to be doing nothing but convolution networks. Your homework will be convolution networks. It's very likely that by the end of this time, we'll be close to picking a project. We'll probably end up picking a project around convolution networks because you'll learn so much about them. They're very cool, very powerful. There's lots left to learn. Anyways, I'll just stop it there. I'll take any questions or Not, I will see you on Thursday. Questions? Yeah.
Yeah. So I kind of get like how you do classification for images. What if you wanted to extend that to classifying actions in a video, right? Like, is there an intuitive extension?
So what is, what's classification of an image, right? It's just a label saying that that a horse is in this image.
Yeah.
So in the same way, you take, a segment, a video segment, however long it needs to be, and you label that saying there is this action in this segment. That's it. You're just labeling that. Now you might want to get more specific about like a parameterization of the action, a karate chop or something. You might actually want to track what's happening with the hand, but then you need labels that tell you about tracking that, right? That's whatever it is you're trying to learn, you just have to have labels for it. Other questions? Okay. Luck on the homework.
Before going, two things. First of all, come to our office hours when you have questions, please. Really, we haven't seen a lot of you, and I know that many of you have questions. So please, or email us. Second thing, I put a few instructions on the homework webpage to submit the homework. Please follow them. They are very easy and they will make things easy for us. That's all. Bye.
It's just going to be an enormous there's all this information that's like